Good day, dear friends. My name is Evgeny Proskrin. I'm the founder of A.T.F Group. This is an engineering and manufacturing group of companies that started in a garage, producing hardware for transformers. And now it offers digital solutions for a wide range of industrial sectors. Today we are launching a series of micro lessons to share practical knowledge and help our energy sector operate more reliably, efficiently, and safely. After all, our mission is simple: your energy under our protection. In the previous video, we learned how to calculate the capitalization of losses and evaluate the economic performance of a transformer. Today, we conclude the series by combining technical and economic logic. We'll explore how transformer design is optimized, where losses can be reduced when it's worth the cost, and which decisions engineers make during the design phase. The goal of optimization is simple: increase the economic efficiency of the transformer without compromising reliability or standards, reduce capitalized losses by refining the design and selecting better materials, and most importantly, find the balance between manufacturing and installation cost, size and weight, no load and load-related energy losses. Common optimization methods include enlarging winding cross-section. This reduces current density and load losses, but increases copper weight and size. Using transposed conductors, also known as CTC, reduces eddy current losses in windings, especially when current density exceeds 2.5 amperes per square millimeter. Using high permeability steel, such as 0.23 millimeter thick sheets with specific losses under 0.95 watts per kilogram at 1.5 Tesla, decreases no-load losses. Optimizing core geometry by reducing air gaps and distributing cross-sections more evenly minimizes stray magnetic fields and structural losses. Installing shields and magnetic shunts in areas of leakage further reduces additional losses. However, every improvement affects cost and mass. For example, increasing copper cross-section by 15% leads to a 12% increase in winding mass and a 10% increase in cost. Using higher-grade steel raises the core price by 5 to 8%. Installing magnetic shields and shunts can enlarge dimensions by up to 2%. But these changes can reduce losses by up to 20% and cut the capitalized loss cost by tens of thousands of rubles over the transformer's lifetime. Now let's look at a real-world example. We have a 160 megavolt ampere transformer. The base version has no load losses of 6.3 kilowatts, load losses of 14.5 kilowatts, a total weight of 63 metric tons, and a manufacturing cost of 4,200,000 rubles. The optimized version has no load losses reduced to 4.8 kilowatts, load losses down to 11.2 kilowatts, a weight of 67 metric tons, and a manufacturing cost of 4,450,000 rubles. The capitalization coefficients are Kay Wye equals 3,100 rubles per kilowatt for no load losses, X 2,000 rubles per kilowatt for load losses. Now let's calculate capitalized losses. For the base model, 6.3 kilowatts multiplied by Kay Wye, that is 3,100, equals 19,530 rubles. 14.5 kilowatts multiplied by 2,000 equals 29,000 rubles. Adding both values, the total capitalization equals 48,530 rubles. For the optimized model, 4.8 kilowatts times KY, which is 3,100, equals 14,880 rubles. 11.2 kilowatts times 2,000 equals 22,400 rubles. Total capitalization, 37,280 rubles. The difference between the two models is 11,250 rubles saved over the service life. However, the optimized version costs 250,000 rubles more. This means the improvement is not economically justified unless the cost of electricity increases or if the transformer operates for significantly longer than 25 years. Let's now calculate the cost-effectiveness ratio, also called KO. This ratio equals the difference in capitalized losses divided by the increase in manufacturing cost. That is, 11,250 rubles divided by 250,000 rubles. The result is 0.045. Conclusion. At the current KY value, the optimization is not yet worth it. But if KY rises above 7,000 rubles per kilowatt, the cost-effectiveness ratio approaches 1, and the optimization becomes economically viable. Now let's discuss how to find the optimal decision point. Imagine a graph. The horizontal axis shows increased transformer cost. The vertical axis shows reduced capitalized losses. The lowest total ownership cost is found where the sum of the manufacturing cost plus no load losses multiplied by KY plus load losses multiplied by KX reaches its minimum value. Sensitivity analysis is also important. We analyze how changes in KY or KX affect the outcome. We also examine what happens if the transformer runs for less than 25 years. For example, just 15 years. Your practical assignment: you're designing a 100 MVA transformer. Compare two options. Option A, cost 3,600,000 rubles. No load losses, 5.8 kilowatts. Load losses, 13.2 kilowatts. Option B, cost 3,850,000 rubles. No load losses, 3.9 kilowatts. Load losses, 10.5 kilowatts. Capitalization coefficients. KY equals 2,950 rubles per kilowatt. KX equals 1,850 rubles per kilowatt. Now calculate. For option A, 5.8 times KY, that is 2,950 equals 17,110 rubles. 13.2 times 1,850 equals 24,420 rubles. Total capitalization equals 41,530 rubles. Total cost of ownership equals 3,641,530 rubles. For option B, 3.9 times KY, or 2,950 equals 11,500 rubles. 10.5 times 1,850 equals 19,425 rubles. Total capitalization equals 30,930 rubles. Total cost of ownership equals 3,880,930 rubles. Let's now calculate the efficiency coefficient, KO. Take the difference in capitalized losses, that's 41,530 minus 30,930, which equals 10,600 rubles. Divide that by the cost difference, 3,850,000 minus 3,600,000, which equals 250,000 rubles. The result is approximately 0.0432. Final question. At what value of KY does option B become more cost-effective? The calculation is shown on screen. Today we've seen how technical and economic considerations merge in transformer design. We evaluated how to reduce losses, calculated investment payback, and learned when an upgrade is worth the cost and when it isn't. These insights help engineers justify every gram of copper and every millimeter of steel with numbers. In the next module, we'll shift to a new topic: thermal operating conditions. Even the best optimized transformer can fail without proper cooling. And thermal balance. Lesson 5. Point 1 will open this topic and show how temperature shapes transformer lifespan. Want to explore the topic in more depth? Visit our website. The link is in the description. Interested in real-world solutions and industry challenges on this topic? Contact us. Our details are on the screen. Want to become a part of the global energy flow? Reach out to us. You'll find our contacts on the screen.